nuclear physics, tools and the techniques applied to nuclear physics. So let me first thank the organizers for inviting me to this nice place. And then I will begin by some consideration about nuclear energy. Then I will try to show you what nuclear physicists can bring to the domain and present some results about nuclear physics, nuclear energy related data taken by recently. So some consideration about nuclear energy. So 10 years ago, it was expected that there will be a big renaissance of nuclear energy because of the increase of nuclear energy demand and concern about CO2 emission. But this has not happened yet because of two high demand of energy, and in particular electricity generation. And because of the CO2 concern, the solution is not only in energy saving in renewable energy, because energy saving and increase of energetic efficiency is important, but is limited when you will have achieved the maximum saving that you can do. Nothing can be done else. And this is counterbalanced by the increase of demand from developing countries. Renewable energy are, of course, one part of the solution, but for the moment, they are still intermittent and they are still very expensive. So nuclear energy can certainly continue to play an important role, although there is a fear of accident and the question of waste which has to be solved. And also in some countries, in particular in European countries, people have decided to get off nuclear energy. If you look at what is the present situation about reactors, so here is a table of all reactors which are operating in construction, planned or proposed in the world. And you see that in the presently there are 65 reactors which are in construction, of which 33 in China, 9 in Russia, 6 in India, and reactors which are planned, which means that they are already ordered. There are 165 reactors which are planned for the coming years. And of course, most of them are in Asia or in Russia, but there are also some of them in US, which are planned, and in European countries. So for all these reasons, it's clear that nuclear energy will continue to develop and probably will develop faster in the coming years. But this is true only if confidence is restored, waste question is settled, if it is economically competitive, and in the long term, if the question of resource in uranium is also addressed. This means that since the uranium resources are limited, we have to go to a generation 4 reactors in which you can use natural uranium and with plutonium, and this will multiply the resource by a factor 1,000 mostly. But this is a question that will arise only on the long term. So if we look at the situation of reactors, so we are now operating generation 2 commercial reactors. There are new reactors which are called generation 3 or generation 3 plus, in which mainly the safety has been improved, it has been optimized, but it's mainly the same types of reactors. And people are working for generation 4 reactors, which would have enhanced safety, which would be able to burn some of the waste they produce, and which should be also proliferation resistant, and also can address the question of breeding plutonium for longer term resources. So concerning the nuclear waste management, as I said, this is a question that the general public is very much concerned about. So it's clear that spent fuel is very radiotoxic. So here is a relative radiotoxicity of spent fuel compared to the natural radiotoxicity of uranium ore. Here, without doing anything. Here you see that if you remove plutonium and recycle it, for instance, in MOX fuel, as is done in France, you reduce a lot the radiotoxicity and the time during which it is more radiotoxic than uranium ore. And if you remove all minor actinides, then you end up with only the radiotoxicity due to fission products that are very difficult to transmute. So people have more or less given up the idea of recycling fission products. But by removing minor actinide, you can gain a large factor in the radiotoxicity and in the time at which it becomes as radiotoxic as natural ore. So so the idea is to transmute minor actinide. So you can do this either in reactors, in critical reactors, but then you can put only small amount of minor actinide in each reactors, because when you do so, you degrade some of the safety parameters of the reactors. For instance, the fraction of delayed neutrons, the Doppler coefficient. So this limits the amount of minor actinide you can put on a reactor. So another solution is to have dedicated subcritical reactors driven by accelerator, and because they are subcritical, you can put larger amounts of minor actinides, and so have only few dedicated systems for transmuting waste. So, for instance, there is a project in Belgium. This is a MIRA project of an ADS, of a demonstrator of an ADS, which is planned. So let me come now to what we nuclear physicists can do in the domain. So for all this issue related to new types of reactor, minimization of waste, transmutation of waste, and so on, there is a need for nuclear data. So there are needs for existing or generation 3 reactors, as for instance concerning optimization of fuel burn-up, increase of lifetime, reducing safety margin, waste disposal. So for this, for instance, means that maybe you will, when you increase lifetimes, so some isotopes which are only present marginally in a classical reactor will become more important. So then you need the cross-sections on these isotopes. Waste disposal, for transmutation of waste. So you need a lot of cross-section concerning minor actinides. For fast reactors, you will have new material, new fuel, new cladding, new coolant materials. You will also try to make actinide transmutation. And for ADS, so ADS is a 1 GeV accelerator impinging on a spallation target. So here you will create a lot of radioactive residues, and so you need also data concerning radioactive inventory of the spallation target, and also data concerning possible material damage in structural material, in particular in the window, which is separating the accelerator and the reactor. So for all this, you need cross-sections, capture, fission cross-section, but also inelastic and XN reactions. You need to know also, for instance, for decay heat generation, to delayed gammas, prompt and delayed neutrons, characteristic of the fission products, and also for what concerns ADS, data about spallation residues. So in the using of nuclear data for nuclear energy, so experimental data are not used directly. They are used through libraries generally. So what is needed are differential measurements. And since it is not possible to measure everything, people have to go through evaluation to build libraries which contain all the possible isotopes at all the possible energy which are playing a role. So differential measurements when they are obtained, they can be used directly in evaluation, but also they can be used for understanding the physics so that nuclear reaction model can be developed. And then the evaluated data library are generated through the evaluation model. And for the high energy part concerning ADS, people are not using library, but they are using directly the nuclear model inside the transport codes for simulating ADS. All this has to be, of course, validated through integral measurements. So most of the things I will show, most of the results I will show are been obtained during a European project. So there was a European project called ANDES, which was funded by the Euratom 7 Framework Program. And now there is a new project which has begun 1.5 years ago, which is called Chanda. And most of the things that I will show are done, have been done within ANDES or within Chanda. So Chanda, just to present it, is a project, it's a European project which contains transnational access to available nuclear energy, nuclear experimental facilities. It has also a part concerning the upgrade of the NTOF and NFS facility, support radioactive target fabrication laboratory, and what we are concerned today is in developing new methodologies and capacity in performing measurements and validation of nuclear data and models. So let me first begin with some examples of results which have been obtained by the NTOF collaboration at CERN. So NTOF has measured a lot of important cross-section for nuclear energy. In particular, they have measured capture cross-sections. I think there is in this conference talk about capture cross-section, but for astrophysics. But they have obtained a lot of capture cross-section. Here I give you examples taken from talk from Nicola Colonna at the last Chanda meeting in April concerning fission cross-section. So here are two examples. One is americium-241, for which data were rather scarce before the end of measurements. And the library were discrepant, a lot of discrepancy between the library. And so for the European library, which is JEF, which was very bad compared to the NTOF data, this has led to a major revision, and now the new release, JEF 3.2, will be based on this NTOF data. And the other example of curium-245, which is an example of an isotope which is important in transmutation of actinide, or when you increase the lifetime of the fuel, for which there was very few data, and with also large discrepancy. And you see that the end of data are very interesting and are much better than existing data, and solve the difference between the two sets of data. Another example of where nuclear physics can play an important role is surrogate reactions. So, as you know, it's very difficult to have targets of highly radioactive material. So there are cross-sections which are difficultly accessible because of the possibility of making a target. And so there is another solution, is to make the same compound nucleus by another reaction. And if we assume that the fission, for instance, the fission cross-section will be the same and is depending only on the compound nucleus, you can access, for instance, here by sending helium-3 on americium-243, you can do, and by transfer reaction, you can have americium 42 plus alpha, and so you can simulate, you can mock up the N plus americium-241. So this works very well for fission cross-section. So this is an example obtained by the collaboration between Bordeaux, IPNO, and CEA about americium-241, where they have compared cross-section obtained by direct measurements and by the surrogate method. So you see that there is a complete fit of the two methods, and so it works very well. And so this is the validation of the method, and here they use it to measure curium-243 and have a very good and interesting result on this nuclei. The question is now, can we apply the same to capture cross-section? So the same group have done a test on known lanthanide capture cross-section to see if capture cross-section can also be measured by surrogate reaction. And there is a big discrepancy between what they have found and what was found by direct reaction. And this is due to the fact that it is not the same population of spin and parity which is populated in the compound nucleus in the direct and in the transfer reaction. So this has to be understood, and maybe if it is understood, it can be used anyhow. So there have been recently new studies made at Oslo cyclotron about an experiment where they try to measure simultaneously fission and gamma ray probabilities. And you see, how, like it was shown before, so this is a case of simulating the uranium-236 capture reaction, that when you compare to the evaluation, which was done on direct reactions, there is a big an agreement for the fission cross-section, but a big discrepancy between capture cross-section. So so this was just a test experiment, and now they will have a new experiment at IPNO with beam of high intensity, an excellent beam energy resolution, because you see here the energy resolution was not very good, and with a segmented fission fragment detector, so they will be able to measure the populations of gamma for both simultaneously, and maybe understand which types of states are populated in the two processes, and then this will help to understand the physics behind. Let me now come to decay heat calculations. So decay heat calculations are very important, as was shown, for instance, by the Fukushima accident. But it's also important if people want to foresee shorter refueling times. It is also important in the case of shielding for the transport of spent fuel, and also, of course, for storage. To be able to predict correctly decay heat, you need, of course, fission yields, because it's the fission fragments which decay by beta emission, which produce the heat. Of course, you need also decay data, that means half-life, branching ratio, and also mean beta and gamma energies. For a long time, there was a discrepancy between calculations of decay heat and measurements of decay heat, as illustrated here, where you see the red curve and the points here, which were discrepant. And this discrepancy has been solved recently. In fact, this was due to the fact that mean gamma energy and mean beta energy were deduced from gamma measurements with high resolution germanium detector, which have very low efficiency for high gamma. So you miss some of the cascade, the high energy gamma cascade, and this ends up in a wrong estimation of mean gamma energy and mean beta energy that you deduce from the gamma energy. By making now measurements with total absorption gamma ray spectrometry using 4-pi scintillation detectors as a calorimeter, you can use the full gamma energy, and then you can solve this problem. So this experiment has been done at Jyväskylä using the Igizol separator and the GFL trap, penning trap for isolating the different isotopes that were studied. And after they have measured all these isotopes and the beta decay and gamma spectrometry for all these isotopes, they were able to reconstruct now a new curve which agrees perfectly with the experimental data. So, so these types of measurements are also important for antineutrino spectra, which can be used for control of proliferation, as I will show later if I have time. Yes, thank you. Yes. Among the things which are much studied by nuclear physicists are fission fragment studies, because, as I said, fission fragments play an important role in decay heat, in radioactive inventory, and their isotopic yield is not well known, and so there are a lot of experiments presently done or foreseen. I will concentrate on two of them, since we are in a nucleus-nucleus reaction, which are done with nucleus-nucleus reaction. So the first one is isotopic fission yield from compound nuclei produced in transfer reaction at Ganil. So this is also examples that I have taken from the talk from Fanny Farget at the Shanda meeting last April. So in this reaction, this is also a surrogate reaction when you can populate compound nucleus that will fission by transfer reaction using carbon on uranium or plutonium, or on uranium, and then you can have access to nuclei above uranium. So, for instance, this is a mass distribution. Isotopic distributions, because each curve is an element, so isotopic distribution of the different fission fragments produced in this reaction at an excitation energy of 10 MeV. So this technique, which uses VAMOS and the identification of the light partner, which is fully identified, allows you to access nuclei above uranium. You can determine the excitation energy, assuming that there is no excitation of the light transfer partner. And because they are using reverse kinematics, you have a high resolution which permits the isotopic identification. And this also gives the velocity of the fragments, so you can reconstruct also the total kinetic energy, and finally the neutron emission as a function of excitation energy. And so here is, for instance, a plot of the mass distribution at different excitation energies that they have measured at GANYL. The second example of fission fragment study is the SOFIA experiment, which is done by a collaboration between CEA, ORSE, GANYL, CNBG, Santiago de Compostela, at GSI. In this experiment, they use the fission of secondary beams in the Coulomb field of a heavy target at GSI. The fission is induced by virtual absorption of photon which excite giant dipole resonance, and this corresponds more or less to excitation energies, yes, of around 12 MeV, sorry, which correspond in the corresponding neutron induced reaction to 6 MeV. So here there is also fold identification, but of both fission fragments for actinides and pre-actinides. So here, compared to the other experiment, the excitation energy, I would say, is less well defined, but there is simultaneous measurement of the two fission fragments. Here also you measure the total the kinetic energy, and you can, by conservation laws, identify also, reconstruct the total kinetic energy associated to the two fission fragments. So here is a plot from that Audrey Chatillon have shown recently of the total kinetic energy distribution as a function of the isotopes produced in the fission of uranium-237. So I will finish by high energy data. 2 minutes, yes. So as I said, spallation reaction studies are important for LES, in particular for the radioactive inventory in the spallation target. And in particular, people are concerned about volatile elements, which can be emitted either in accident, but also it's important for long-term disposal and in case of maintenance operation. In particular, gas production also in structural material is important, and in particular helium, which is produced in high energy in large quantities, and which can produce bubbles and entanglements of material and fragilized material. So for this, we need highly predicted models. So at high energy, as I said, we don't use libraries, but we do use models which are implemented into transport codes. And so we don't measure all data at full energy because it will be too complicated. So we use models which should be, of course, benchmarked against good data. And also we try to understand the reaction mechanism. So as regards new high-quality data which have been produced recently, so let me mention the work done at ITTEP Moscow by the group of Titarenko, who is measuring a lot of excitation functions, that is residue production as a function of incident energy for a lot of different elements and a lot of residues. Here I give an example of residues on iron. And as we concern light charge particle prediction, so a lot has been done in the past about proton-induced reaction. Yes, and yes, 2 minutes. But what is new is neutron-induced reaction, for instance, which has measured at Uppsala, and new data on neutron-induced reaction. So I will not talk about the SOFIA experiment for high energy because you will have a talk by José Bellier later in this conference. And just let me show you an example of the importance of having a correct prediction of codes. This is a production, for instance, of astatine isotopes in the Isolt lead bismuth target, which is mostly due to secondary reaction induced by high energy helium ions, or what was observed in the lead SynQ target, production of polonium isotopes 10 years after irradiation, while polonium has a half-life of 130 days. And in fact, it is due to the decay of lead-210, which is formed mainly by secondary reaction induced by tritium. And for predicting all this, you need, of course, good prediction of the secondary particles, and in particular of the high energy tails of the secondary products like alpha and tritium. And this has been recently implemented in the models, and with the new model, for instance, that we are developing in Saclay in collaboration with Joseph in Liège, we are able, because we have all the correct processes, to predict correctly both the astatine production in Isolde and the PO210 at SynQ. So I will skip the part on the antineutrino, except if you ask me a question. And I will conclude that the expected renaissance that was expected 10 years ago has not yet happened, but I think that nuclear energy will still continue developing and probably develop faster because of the request from developing countries. The enhanced requirement for safety, economical competitiveness, minimization, or transmutation of waste implies for the need for high quality nuclear data and more predictive model. And nuclear physicists are still playing a role and can still play an important role by providing innovative experimental techniques and theoretical models. Thank you.
Is open for question and comments. I have to limit it because we are running out of time, so I'm sorry, but I will take only a few of them. 1, 2, okay?
Yeah, Sylvie, Azayas from Orsay. I have a question concerning nuclear data. You show a lot of data and fit to the data, and actually that's what we see every time on this field. I was wondering whether you involve on these programs theories, because I would think that we have enough data, and sometimes we should support theories to try to have a global improvement of models, rather than have another data. You see my point? I don't see in Shanda, for instance, how much of the funds go to the theories.
Well, for the low energy data, there are evaluations.
No, but
not only, and evaluations are done using nuclear model theory. So there are people, for instance, in Briare-le-Châtel, who are working on nuclear in model development. There is also the TALIS, which is the TALIS code, which is in Shanda also. So there is a work which is in Shanda, and there is a work both in evaluation and in nuclear model development. At high energy, we have a lot improved the nuclear models, and we have worked a lot for the high energy models. What I was showing is that, for instance, for a long time, the data which we were not implemented into library. Now it's not the case. Now the data are used to improve the libraries.
Okay. Okay, I have just a short comment, Sylvie. I think that one of your last slide was on decay heat.
Yes.
I will make myself this a priority program, because I think mastering decay heat modelization and calculation will be essential in designing reactor in the future.
Yeah, yeah.
Okay, let's thank the speaker again. Thank you. Okay, so we're shifting to another important subject in nuclear physics application. And this is Giuseppe Battistoni from Milano, nuclear physics and particle therapy.
First of all, let me thank the organizing committee for having invited me here to speak about the subject of hadron therapy or particle therapy, how it is more often called now. Okay, thank you. Because here in the laboratory of South of INFN, the first experience in Italy concerning particle therapy started, if I'm not wrong, 13 years ago for the treatment of eye tumor. Now, I will give some very short presentation about basic principles, and I will concentrate on relevant aspects of nuclear physics concerning particle therapy, after showing also something about the spread of this discipline throughout the world, and giving some suggestions for future contribution of nuclear physicists to the matter. Let me recall that the NUPEC dedicated a report last year to nuclear physics in medicine, and charged particle therapy plays a fundamental role in this report. And this is a typical case, not being the only one relevant topic of nuclear physics in medicine, but is a typical case where research and clinical application go still together, and in which our contribution might still be important. Why? Because we have to know that there is a significant fraction of people in the medical community that is still not convinced and might have real reason to do that. And the criticism are that hadron therapy, in particular ion therapy, the one with nuclear projectiles, could be too complicated, too expensive, and probably not able to reach the promised goals in terms of precision. Of course, we believe that this is not the case, but we have to help people to demonstrate this. Basic principle, as almost many of you know, the main point is that while conventional radiotherapy based on photons gives you as a function of depth a dose which is maximum at the entrance and then decrease more or less exponentially, heavy charged particle instead deposit energy having a sharp peak at the end of a range, the so-called Bragg peak, so allowing a better localization. And the strategy is that you build a uniform dose distribution in the tumor region by adding together several energies with a proper intensity. So the key point is that charged particle therapy, not necessarily in all cases, is more efficient in terms of deleting tumor cell with respect to normal radiotherapy, but as you can see here in this comparison, at least at qualitative level, where the colors represent the level of dose, charged particle therapy is able to give less damage to healthy tissues, with compared to even sophisticated cases of photon radiotherapy. These are other cases called radiosurgery, even in which in a single shot a high dose is delivered. Even in that case, the possibility of sparing non-tumor tissue is elevated. The first idea dates back to 1946 by Robert Wilson. And actually, the first experiments were performed in the United States in the early 50s. The first patient was treated in Europe at the end of the 50s at Uppsala. And then there is a long story where maybe important milestones are that the first facility dedicated to carbon ion therapy was started in Japan in 1994, and the first European facility which makes at the same time protons and carbon started in Germany at Heidelberg in 2009. This is an interdisciplinary topic. Let me recall you a basic fact. If you consider different kinds of radiation, and if you look at the nanometric scale of energy deposition, while gamma radiation has sparse events, hadrons, in particular increasing the Z, or the charge of the particle, might give a higher density deposition at the DNA scale. Therefore, high-Z projectiles can be more effective in giving non-repairable damages to DNA, thus being more efficient in killing cells. This is expressed by the concept of relative biological effectiveness, which weighs the physical dose, and in practice is a ratio of what you, of the dose that you can release with respect to a reference dose, typically the one that you deliver by means of photons. What it is important to know that in the case in particular of carbon projectiles, you might have this ratio rising up to 3 or 4 at the end of the Bragg peak. By the way, this is a concept that radiotherapists must learn to use. It's not a trivial one. While protons are just like something more than photons. So, in particular, protons are used mostly in this energy range. The relative biological effectiveness is of this order here. They can be accelerated by cyclotron mostly, or synchrotrons. Carbon ions, which is now the other option, is operated in that range. The range of energy is dictated by the amount of depth that you expect to cross. They have a higher efficiency from the biological point of view, so they are well suited for radioresistant tumors. You can get a reduced number of fractions in the treatment, and this is important. You have also having a higher mass, a reduced lateral spread, and this is important in terms of precision. However, they have to be accelerated by larger and heavier machines and also more expensive machines. These projectiles undergo nuclear fragmentation that in some cases can be a nuisance. Of course, you need heavier gantries, magnets, etc. They are accelerated by synchrotrons in general, although you can think also of cyclotrons, but in practice they are not used for this topic. By the way, here a group designed a cyclotron that could be used for ion therapy. There are at least a couple of future options to be considered. The use of helium projectiles. We have a negligible fragmentation with respect to carbon ions. They, in any case, have a slightly larger efficiency, biological efficiency than protons, and with respect to protons, still have a limited lateral scattering. You can think also of oxygen in the case in which you need to deliver a very high concentrated dose to some radio-resistant zone. In the world, in the years, the number of centers dedicated to this therapy is increasing, mostly protons, and also the number of patients. Of course, the total number that you can see here is very little as compared to the total number of people cured with radiotherapy. However, they're increasing. This is the statistic of 2014. Notice that only in the United States, 27 new centers are expected to be built by 2017. In Europe, for instance, in UK, 7 new centers will be built. The statistics of people treated with carbon ions is concentrated mostly in Japan for the moment. This is the first clinical center, important clinical center that operated in the United States, the Loma Linda Hospital, where they make use of a synchrotron and they have several treatment rooms, and they now operate at a pace of about 160 sessions per day, this is, instead is the sketch of the Japanese centers, the center that I was mentioning before, where you see they have two synchrotrons reaching a high energy, because this center is dedicated both to therapy and to nuclear physics research. And this is the first facility in Europe that was started treating the first patient at the end of 2009. That is the Ion Therapy Center of Heidelberg, which has the first rotating entry for carbon ions. Is a very huge object. They are based on a synchrotron. And here in Italy, the Pavia Center was started using a synchrotron built and commissioned with the fundamental help of INFN, CERN, and contributions by GSI and Grenoble. So far, this 1 month ago was the number of patients that has been treated. This design is the base of a new center that is being now starting soon operation in Austria, that is Med-Austria. The modern and more efficient way to deliver those is the so-called active scanning, in which the beam is deflected transversally by a set of magnets, and the depth is, of course, regulated by varying the energy on the cyclotron. And so you can paint, slice by slice, the tumor region in spots, separated. For instance, I can tell you at now the separation between spots is of the order of 2 millimeters. This is the typical intensity of normal machines for proton and carbon ions that is needed now for these treatments. This is the dose delivery system at now, for instance. In Italy, we have now started the proton therapy in Trento. This is instead a cyclotron-based facility with rotating country. This is all industrial because it is built and commissioned by IBA. Hadron therapy and nuclear physics. This is a list of something that we consider the important topics in nuclear physics, which can be a little bit different between proton therapy and therapy with nuclei. Of course, reaction cross-sections are important, but now, as I will try to demonstrate, also the capability of predicting and understanding the emission of secondary particles could play a significant role. Let me start with a basic thing that is the physics of Bragg peak. Consider the beam coming from below. Longitudinally speaking, you have this, that of course is dominated by ionization energy loss, but nuclear physics plays a role because the shape is modified by nuclear interactions. In particular, you can take away those from here upstream. And in particular, nuclear interaction also dominates the lateral scattering, and this is important in a therapy that aims to precision. This is something taken away by a publication this year by Tommasino and Durante, that gives you some numbers in a proton therapy. In practice, in a typical treatment plan, 20% of protons undergo nuclear interaction, and 60% of the energy is locally deposited by charged fragments, and you have 40% of something, mostly neurons and photons, that go away out of the field of treatment. In the case of nuclear projectiles, there is, this effect that since the primary beam is attenuated because it fragments, there is, as a function of depth, a build-up of fragments which, having a lower mass, go faster and go beyond the range. And this has to be considered and could be important when you have to treat something close to an organ at risk. By Monte Carlo, you can try to guess, understand how the population of this fragment is composed. Of course, you are dominated by light particles. Predicting the fraction of different things is important because different nuclear spaces have different biological effectiveness. But nuclear physics, as I told you, is important also for lateral scattering. Take into account that the treatment planning, that is the software that medical physicists run in order to plan the treatment, is normally based on analytical approximation. And at present, for instance, using 2 or 3 Gaussians, this in green is what they normally make use of. But neglecting these details that, of course, in the logarithmic scale you might think they are negligible, but in the long run, this is something that you have to consider. Nuclear projectiles are also important because, as I was mentioning before, the lateral spread of a beam as a function of depth is considerably lower for carbons with respect to protons, but even helium, as you can see, has a tremendous advantage with respect to protons. Uncertainties. The first fundamental uncertainty that people say is one of the main obstacles to the diffusion of hadron therapy is the uncertainty on the knowledge of the range of particles. In particular because one is based on medical imaging based on photons which undergo different reactions. So at experimental level, one important suggestion is why instead of making tomography with photons, don't we have tomography made with protons? And this is something that is different groups in the world are trying to solve. The question is not trivial because while photons do not suffer from multiple Coulomb scattering, this instead is the case of protons. This is the approach by a group here in the INFN in which for the moment, using rotating phantoms as a test, one tracks protons with silicon trackers and measure the residual energy with a calorimeter. This is the result of a test that was performed here at low energy. This radiography with protons has to be done with a maximum energy of protons, which must cross the patient. So think of 250 MeV. This is a test performed at 60 MeV, in which a phantom with different insert densities was explored moving vertically. And if the animation starts, you can see what you can reconstruct, and you can see moving the different zones of the phantom. At some time, you will see appearing the place where two high-density objects are there. So I stress once again that here software plays software reconstruction plays a fundamental role. Now, other things that are important. You may have different other sorts of uncertainties. Most important one are anatomical variations from fraction to fraction or during the same fraction within the patients. For instance, suppose that before the tumor sometimes an air gap appears. You modify the distribution of those. In the case of normal radiotherapy, the effect this is a qualitative sketch, of course, is negligible. But in case of hadron therapy, you might create some problem, giving more dose to the healthy tissues and not covering completely, for instance, the tumor part. Therefore, the need for some online check, online monitoring of therapy is something that the community of medical physics considered an important goal in the last, let's say, 5 or 6 years. And here, nuclear physics gives us some tools to be explored, because thanks to the nuclear interaction, we have different products. In particular, you might think of the production of beta plus emitters, and so you can detect the annihilation photons from beta plus decay. But you have also the gammas from nuclear de-excitation, and even charged particles that can get out from the patients in real time. For instance, let me show a result. This is the activity measured in beam during a treatment on a phantom with several energies, a complete plane, in which in the phantom at some time was inserted an air cavity. And you can see the black one is the experimental measurement that in a short acquisition time, after, of course, you need some time for the build-up of activation, you can spot the presence of the cavity. By Monte Carlo, you can learn what is the contribution of different beta plus emitters, of course. This is considered a sort of baseline solution, but has problems. You have to go really in beam, otherwise online. Otherwise, you can suffer, for instance, from what is called a metabolic washout, in which metabolism of the body can blur the distribution of these emitters. But the problem when you go online that you also suffer from the many particles that in any case exit and then can spoil the working of your, the operation of your readout electronics. For instance, in this case in which we worked as a synchrotron at now, we made use of acquisition between one spill and the other in order not to be blind from all the rest of the particle. Same thing was performed later at now with carbon ions also, in which two different cavities could be spotted in the longitudinal profile of activation. The other solution is prompt gamma de-excitation. That is an important source of, because there are many. This is a result of a test performed by Lyon group at low energy in a 95 MeV per nucleon. And from the results, you can see what is the capability of associating the longitudinal profile of emission of gammas with respect to the position of Bragg peak. Let me also show this figure from a recently appeared paper by French colleagues, in which they demonstrate how they can spot, using the reconstructed profile of emission of the excitation photons, how they can spot the presence of different inserts of different density. Here the question is detection technique. There are different solutions that suffer from different kind of problems. I want just to mention that now ABA has prepared something ready for market to be used in proton therapy to monitor with gamma rays hadron therapy. Let me stress that it is extremely important in this case to have a Monte Carlo prediction of what you are going to expect in a complex geometry. This is something that normally treatment plans do not provide. You need to calculate yourself. How many particles get out from the patient? This is again a Monte Carlo calculation of mine from the real treatment of a patient at now. And here I show as a function of the angle of emission, this is in a carbon therapy treatment. For instance, how many neurons, about 20 MeV fast neurons exit, how many protons, other fragments, etc. There are enough things for which you can think about also using charged particles. And in particular, let me quote this experiment published 1 year ago, of the measurement of charged, mostly protons, coming out from a PMMA phantom at 90 degrees, and you can get this kind of flux of protons for each normalized to 1 carbon ion, and it can be shown that you can make a sort of, using protons, a radiography of what is really happening with your beam inside the target. Future options. This is something designed with a beam. This gives you a practical idea how increasing the mass you can be more precise, laterally speaking. This I already mentioned. Heidelberg is already ready to use both helium and oxygen. We made some experiment to measure integrated fragmentation in a target by helium beam. Here are some results in which you show the different bands of fragments detected at a small angle in the forward direction. And also, again, the capability of measuring protons coming out at different energies at 90 degrees or large angle in general, showing the capability of spotting the increase of energy and the increase of range. Some words about Monte Carlo. They are becoming more and more fundamental because they are needed for the understanding of the facility and beam lines. They are needed to commission treatment planning. They are important for verification and correction of treatment planning in the case of complex geometries. They are used to understand what happens when you get out from the water equivalence approximation. They allow you to have a real 3D tracking in a detailed description of the actual geometry. And they allow you to understand what is really coming out from your patient and study detector response. Of course, the challenges are the nuclear physics model, and here I must add the coupling with the radiobiological models. And this is something that goes beyond nuclear physics, but something to which nuclear physicists contribute. Of course, technologically speaking, computing time. There are a list of things that is important to improve in the models. Still, there is, in particular, the issue of understanding fragmentation in sometimes remains an open issue. In any case, a huge progress has been made in the most important codes used in this topic in the last 10 years at least. Just to give you an example, these are the cross-section to produce carbon-11 and oxygen-15 as you get from existing database. You might see that experimental errors are still large. For them matching, we make use of a sort of average, but this maybe could be improved. This is the conclusion, a list of things that nuclear physicists can do, according to my choice, in order to help this discipline to improve. For instance, go towards Monte Carlo treatment planning instead of analytic one. This requires a continuous model evolution and validation, and possible, if more experimental data could be available, would be nice. We are going towards very fast treatments. This requires higher intensity beams. notice that at some point the neutron dosimetry could be something more important than it is today. One has to go towards the treatment of moving organs, to the need of going to treatment done in single fractions. In that case, the check of range is fundamental, because if you are wrong in a single fraction, you have lost. Then, personalized medicine. One can go to something in which instead of giving a uniform dose, you could give enhancement to that particular region that are considered radioresistance, or going towards image-guided iron therapy. And this requires a lot of improvements in imaging, also in modeling, and also in computing. Not to speak about all the issues in accelerator developments, because in order to make this discipline competitive, we need more compact, less expensive solutions, and new systems. For instance, here there is an important group developing new efficient ion sources that could be useful for this topic. And maybe, who knows, we could have in the future new solutions for compact facilities like those based on plasma acceleration driven by laser. Who knows? And with this, I think I can conclude, thanking a lot of colleagues who has provided me with material.
Thank you. We have time for some questions or comments.
Yeah, I believe organ moves the day and night centimeter, right? Any organ, in the morning and night. So why you need such a narrow beam with oxygen or carbon?
I'm not sure I understand.
You understand what I mean?
Can you repeat, please?
Yeah, organ normally moves the day and night easily by centimeter, right? It's not stay millimeter scale. So why you need a carbon or even oxygen to make a lateral spread smaller?
Consider that the most relevant diseases for which carbon and proton therapy as well are now used are for the head and neck region, where you have no movements, and in which if you can improve the quality in the sense of those not delivered to the normal tissue, you increase the benefit of ion therapy.
Yeah.
The proton CT you showed was based on a silicon tracker, which I don't normally think of as a radiation-hard material. Can you comment on the robustness of the instruments?
You don't need high intensity. You must not use high intensity for proton CT, because you have not to deliver high dose to the patients for imaging. Consider that you are going to use the highest energy in order for protons to cross the patients. So the black peak is outside the patient, so this helps. But you can go with 110 or less of the intensity that you would use for a normal treatment.
The neutron is a hadron. You didn't say anything about neutron therapy.
Just because of time. So.
That's not true. That's not true. Okay, go ahead.
No, but it is true that at some time, the question of understanding, especially for long-term effects, what is the contribution of neutrons that, of course, are produced in a huge quantity in this kind of therapy, will be considered. For the moment, this is something that I have to say is neglected, because in any case, the dose locally delivered by neutrons is still low as compared with the rest. However, I stress again, if we want to consider possible long-term effects, the question of neutrons, especially in treatments where large part of the body is considered, will need to be carefully studied. But that's a different thing. That's a different thing. Ah, okay. Sorry, I didn't.
Okay.
Yeah, if secondary neutrons are a problem, it looks like the best beams would be proton-rich exotic beams. Is there any discussion of that? They would give you your PET capability, and they would reduce the neutrons.
I don't know if I'm able to answer, but in any case, let me stress once again that here the key problem in front of the community is to go to some solution that can be not expensive, well under control. So, let's say, standard beams for the moment have to be considered, of course.
Okay. So
But this is a future
the last question will be here. Sorry, Livius.
So I think a promising technique is to use targeted delivery of some chain alpha emitters. I mean, this is also worked in some nuclear physics community because of the fact that they're really targeting just the tumors and eventually tumors when they are spread out. That should not be forgotten.
Of course, I agree.
Okay, if there is no more questions and comments, thank you. Thank the speaker. Thank you. If you give me a